This is going to be another video on oscillator design, and today we're going to take a look at the Colpitts Crystal Oscillator. Now, pretty much any oscillator can be broken down into two main sections. You have an amplifier and a feedback network, which feeds the amplifier's output back to its input. And this feedback network is usually designed to only feedback signals at a particular frequency, because you usually only want to oscillate at one particular frequency. Now, the basic criteria for oscillation is known as the Barkhausen criterion, and it states that the total loop gain, in other words, the gain of the amplifier times the gain of your feedback network, has to be greater than or equal to 1. In other words, you have to actually be amplifying a signal and feeding it back, not attenuating it. The other criteria is that the total phase shift has to be 0. In other words, the signal that you feed back to the input has to be in phase with the original signal that appeared at the input. And the Colpitts oscillator is no exception to these rules. So for clarity, I've redrawn the typical Colpitts oscillator schematic to very clearly segregate the amplifier from the feedback network. And if we take a qualitative analysis of this, we can see that the amplifier here is just an emitter follower. There's really nothing particularly special about it. All the magic, if you will, happens in the feedback network. Now remember that above its series resonance point, a crystal is going to be primarily inductive. So effectively, we have a very high Q inductor here connected across these two capacitors. So there's going to be some frequency at which this inductance resonates with these two capacitors. So we really just have a simple resonant tank circuit here, and that's what gives us the frequency selectivity in this circuit. Now another thing that we need is a phase shift of 0. And since this is just an emitter follower, we know that its output will be in phase with its input. So as long as there's no phase shift through this feedback network, we will also satisfy that criteria as well. Which means the only thing left to satisfy for this to oscillate is that the total loop gain needs to be sufficient. It needs to be greater than 1 in all practical purposes in order to start oscillation. So let's consider the gain in terms of voltage. I've labeled this point here E1 and this point E2. So this is the output of the amplifier and the input to the feedback network, and this is the input to the amplifier and the output of the feedback network. Now by definition, voltage gain is simply the ratio of the output voltage to the input voltage. And if you're at all familiar with emitter followers, you'll know that this ratio, E1 over E2, is actually going to be slightly less than 1. So the voltage gain out of this amplifier is actually going to be a little less than 1. Now if we take a look at the feedback network, its gain in terms of voltage is going to be E2, which is its output, over E1, which is its input. Which means that E1 over E2 times E2 over E1 needs to be greater than 1. Now obviously this is a completely passive network, so it cannot provide any power gain. However, it can transform power in order to provide voltage gain. And while it's true that an emitter follower doesn't have voltage gain, it does have current gain, so there is a total power gain here. So let's take a look at the feedback network in isolation to understand how it works. We have an input voltage E1 and an output voltage E2. We have the capacitive reactances of C1, which is JX1 here, and C2, which is JX2 here. These are capacitive reactances, so they are negative. And of course we have the crystal. Now the crystal, as I mentioned before, is going to be operating primarily as an inductor. So it has an inductive reactance here, JXE, and it also has some internal losses represented by RE here as well. Now when a voltage is applied to the input, there's going to be some current I that goes through this circuit, and some of it's going to go down here through C2 to ground, and some of it will go through C1 and the crystal to ground. So let's just throw some numbers out there. Let's say that E1 is equal to 1 volt. And just to make the numbers easy, let's make the capacitive reactances of both C1 and C2 equal to negative 100 ohms. And since the crystal's inductance is resonant with the capacitance across it, we know that it's going to be equal in magnitude to the sum of the capacitive reactances. So it will be 200 ohms. And just to keep things simple, we'll assume that RE is 0 ohms, which actually isn't a terrible assumption considering that the crystal is pretty high Q and RE tends to be pretty small anyway. So we can just apply Ohm's law here. If we have 1 volt connected across this impedance, we can determine the current by simply taking the voltage of 1 volt and dividing it by the total impedance, which, if we sum this all together, it's 0 plus 200 plus negative 100. So we have 1 divided by 100. And of course, that just gives us 10 milliamps. Now, we can also determine the voltage at E2 using Ohm's law. That's just going to be the current, 10 milliamps, times the impedance, which is 200. So we're left with 2 volts on the output. So this all has to do with impedance and resonance. And we do actually get a voltage gain here due to the negative reactance and positive reactance that we have in this circuit. And I have just such a circuit built up on the bench. I've got a 5 megahertz crystal here, as well as my C1 and C2 capacitors, both of which are 330 picofarads, which is right about 100 ohms of impedance at 5 megahertz. I'm feeding the junction of those two capacitors with a signal from my function generator, so we can monitor the input and output signals from the circuit as I sweep the function generator right around that 5 megahertz frequency. Alright, now I'm feeding a 1 volt peak-to-peak signal into the circuit, and we can see that here in channel 1, and we can also see the output on channel 2. And you can see right now both of these signals are in phase and of the same amplitude. So what I'm going to do is I actually have the frequency set a bit high. It's a bit above the resonant frequency of the circuit right now by about 100 hertz. So I'm going to roll that down, and we'll see what happens as we approach the resonant frequency of the circuit. We can see the output there is starting to grow. And the closer we get to the resonant circuit, the faster it grows. And we're at about a gain of 2 there, just as we'd expect. Now, interestingly, if I keep lowering the frequency, my gain increases here, but you can see we're starting to get a little bit of a phase shift here between the input and output. And in fact, very rapidly flips almost a full 180 degrees here as we go below the resonant frequency. So the frequency that we're going to oscillate at is the frequency at which we have no phase shift and gain. So even though we have more gain here, we're not going to oscillate at that particular frequency because we're starting to get this very rapid phase shift between the input and output of the circuit. And we can more formally define this by stating that E2 is equal to the current going through the crystal, I, times the total impedance of the crystal, which is Re plus JXE. And likewise, we can define E1 as the current I times the series impedance of negative JX1 plus Re plus JXE. Now, of course, E1 could also be defined as the current through C2 times the impedance of C2, negative JX2, but it's actually more convenient to put both E1 and E2 in terms of JXE. And we can see why when we substitute those values into our gain equation for the feedback network, which is just E2 over E1. Now we can see that we have a common term I in both the numerator and denominator, so that'll cancel out. And we're just left with the gain equals Re plus JXE over Re plus JXE minus JX1. But remember, we're dealing with a tuned circuit, so our crystal's inductive reactance, Xe, is going to be equal in magnitude but opposite in sign to the sum of the C1 and C2 impedances. So we can substitute that into our equation, and in the denominator we have a plus JX1 and a minus JX1, so those cancel out, and this is equivalent to Re plus J times X1 plus X2 over Re plus JX2. However, remember, Re is usually very small, and to simplify this equation, we can just assume it's 0. That eliminates Re from the equation altogether. The common J term in the numerator and denominator cancel out, and the final gain is simply the impedance of C1 plus the impedance of C2 over the impedance of C2. And this result should not be terribly surprising. C1 and C2 form a voltage divider between voltages E2 and E1. So the relationship between E1 and E2 is going to be governed by the standard voltage divider formula. which tells us that E1 is going to be equal to E2 times the impedance of C2 divided by the impedance of C1 plus C2. And if we rearrange this equation in terms of E2 over E1, which is the gain of our feedback network, we see that we get the exact same equation that we just derived. So what does this mean for us in terms of the oscillator gain equation? Well, we know that if we make x2 very small and x1 very large, we'll get a lot of gain in our feedback network. However, we can't ignore the gain of our amplifier because it is the product of these two gains that must be greater than or equal to 1. Now, we know that for an emitter follower, the gain is always going to be less than 1. However, what happens if we make x2 very small? Well, C2 is basically a shunt across this emitter resistor, and the smaller its impedance gets, the more it looks like a short circuit to ground. So the voltage here, which is at E1, which is the output of our emitter amplifier, will start to drop as we make C2 very large and its impedance becomes very small. So there is a practical limit on how small we can make the impedance of C2, because at some point this voltage drops so much that the gain of our feedback network can't make up for it in order to satisfy our gain requirements. Now, the voltage gain of an emitter follower amplifier is pretty well defined. It is the transconductance of the transistor itself times the load seen looking out of the emitter, divided by 1 plus the transconductance times the load. So we can see that this will never be 1. It'll always be slightly less than 1. However, as the product of GM and ZL gets very large, we get closer and closer to 1. Likewise, if their product is very small, then we get farther and farther away from 1. We get the actual gain reduces. So we want to make sure that the product of the transconductance and the load seen looking out of the emitter is large in order to get the most voltage gain out of this amplifier. Now, if we examine the load seen looking out of the amplifier's emitter, we of course have the emitter resistor, our feedback network, which we've seen before, and we have the input to the base of the transistor, since we feed this back into the input of the amplifier. However, we usually want the input of the amplifier to be a very large impedance, so that we present a very high impedance load to the crystal, so that we don't load it down and we have a nice high loaded Q. So usually the emitter resistor is large and the input to the base is large as well. So to simplify the analysis, we can just ignore those, leaving us with just the feedback network as the load presented to the emitter of the amplifier. And this is simply the impedance of C2 in parallel with a series combination of the impedance of C1 and the impedance of the crystal, which is JXE and RE here. So if you've ever combined parallel resistances, you know how to combine these parallel impedances. It's just going to be the product of the two parallel impedances divided by the sum of the two parallel impedances. So that means that our load impedance is simply going to be negative JX2 times the sum of RE, JXE, and negative JX1 divided by the total sum, RE plus JXE minus JX1 minus JX2. But remember, at the resonant frequency, the reactance of the crystal, which is inductive, is going to be equal in magnitude but opposite in sign to the sum of the capacitive reactances in the circuit. So we can substitute our XE with X1 plus X2, and this greatly simplifies our equation because X1 cancels out in the numerator and everything in the denominator except for RE cancels out. So this is equivalent to negative JX2 times RE plus JX2 over RE. But we can go a step further. Let's multiply out the numerator here. We see that we have a negative J squared. Again, J squared is just negative 1. Negative 1 is 1. So that simplifies to negative X2 times RE plus X2 squared over RE. Now we have a common X2 term here in the numerator, so we can kind of rearrange this to be X2 times negative JRE plus X2 over RE. However, remember, Re is usually very small, and if we assume that it's much smaller than x2, then for all intents and purposes, we can set it to 0 in the numerator, which completely eliminates it, and leaves us finally with the load impedance is approximately x2 squared over Re. Now this equation tells us a couple of things. First of all, x2, which is the impedance of C2, dominates the load impedance for the most part. So if we make x2 very small, for example, we will have a very small load impedance. And ultimately, a very small load impedance will lead to a very small output from the amplifier. And we already kind of knew this from a qualitative analysis, but it's always nice to have the math to back it up. The other thing you'll notice is that our load was comprised purely of our feedback network, which had a lot of J's in it, right? We have a lot of reactances here. However, all of those J's have gone from our final equation, which means that this is a purely resistive load seen by the emitter. And if our load, which is our feedback network, is purely resistive, then we will get no phase shift through our feedback network. And this is exactly what we need in order to maintain oscillation. We need 0 phase shift and a total loop gain greater than 1. Now, of course, we've made some assumptions and approximations here, and this will only be valid at the frequency of oscillation. So this is the final loop gain equation for the Colpitts oscillator. However, it's not usually presented like this in textbooks because with a little bit of algebraic manipulation, you can simplify and show that the product of your transconductance, your C1 impedance, and C2 impedance has to be greater than or equal to the resistive losses in the crystal. For all intents and purposes, this is what we have to satisfy in order to ensure oscillation. And this is a very useful equation because it's a very easy check to make sure that you have sufficient gain in your loop to overcome the resistive losses in the crystal and get oscillation. So, with all that said, let's take a look at some of the concerns you need to think about when you're actually doing a practical Colpitts crystal oscillator design. So the first thing you want to concern yourself with is transistor biasing. How do we want to bias this transistor in the circuit? And the transistor biasing directly affects the loaded Q of the crystal when it's placed in circuit. So we need to take the loaded Q of the crystal into account as well. How much loaded Q do we need? How much stability do we need? What's the load capacitance that we want to present across the crystal? Many crystals specify that they might need 18 or 20 picofarads of load capacitance across them in order to oscillate at their marked frequency. So we may need to give that particular capacitance if we really need that specific frequency, or we might not care if we're off by a few kilohertz, and then it doesn't matter so much in terms of the frequency of oscillation. But this also directly affects the loaded Q. So again, we have to take the loaded Q of the crystal into consideration here. Also, don't forget about stray parasitics. We've pretty much ignored these up to this point, but you're going to have some internal base emitter capacitance here, which is directly across our C1, and the crystal itself has some shunt capacitance across it as well. What kind of power output do you want from this oscillator? Now, typically with a Colpitts oscillator, the output is taken from the emitter here because that's the lowest impedance point in the circuit, so you get the most power. But this is also directly affected by things like the selection of our C2 capacitance, because if this is a large capacitor with a low impedance, we're going to have less voltage available here at the emitter, as we've already seen. So selecting our load capacitance that we're going to place across the crystal has a direct effect on the power output. And of course, this affects loop gain as well, as does your transistor biasing. So we have to set up our transconductance and select our C1 and C2 capacitors appropriately to ensure that we get reliable startup of oscillation under all of our operating conditions. So let's start off by biasing the transistor. Now, when you're setting up the bias points on your transistor, you want to make sure you take into account the changes in your transistor over temperature. So with a typical BJT, for example, as temperature increases, your base emitter voltage is going to decrease at about 2 millivolts per degree Celsius. So what we want to do is minimize the effect that that change in VBE has on our collector and emitter currents, because the transconductance of the transistor is directly affected by the emitter current. And of course, the transconductance directly affects the loop gain of the oscillator. So we definitely want to minimize that effect. So the easiest way to do that is to set a larger quiescent voltage here on the emitter. The larger your quiescent emitter voltage is, the less of an effect that change in VBE will have on the current going through your collector and emitter. So I'm just going to pick about half rail here. I'll put the emitter voltage at about 4.5 volts, which means that I'm going to have to set up my base bias to be about 5.1, 5.2 volts. And I'm just going to initially set the emitter current at 1 milliamp. Now you can set this higher or lower as your needs require, but 1 milliamp is kind of a good starting point. So that means I need to select an emitter resistor of about 4.7K. It's going to be a little less than 1 milliamp, but it's pretty darn close. And that's also going to determine my transconductance for the amplifier. And at room temperature, the transconductance of a typical BJT is about 1 milliamp, since we have 1 milliamp of emitter current, divided by 26, which gives us 0.038. So now let's select the base biasing resistors. Now, we have two different requirements here for the base resistors. Obviously, whatever we select for these, the voltage divider that they provide needs to set the base at 5.2 volts, but we want these to be relatively large so that the crystal sees a relatively large input impedance looking into this transistor, because these are primarily going to set the input impedance of the transistor. However, the beta of the transistor is not very well defined. It varies over manufacturing tolerances as well as temperature. So we want to make sure that these are small enough so that we have enough current going through our base resistors such that if there's any small variation in the current going through the transistor due to changes in beta, that they're negligible. So a good rule of thumb is to select these resistors such that their parallel combination is not more than 10 times your emitter resistor. So selecting a larger emitter resistor means we can select larger base resistors, which means we have a larger input impedance, which means we have a better loaded Q. So this is another advantage of setting a larger quiescent emitter voltage. With a larger voltage, we can select a larger resistor here to get our desired current. So I've selected 82K and 120K here. That should give us a voltage divider that provides just about spot on 5.2 volts at the base, and their parallel combination is just about 10 times the emitter resistor. So finally, we need to select our C1 and C2 capacitors. Now again, I mentioned there's going to be a base emitter capacitance internal to the transistor that we want to take into account, and that's going to actually vary. So we want to make sure that any variances in that capacitance have a negligible effect on the rest of our circuit. So I usually select C1 to be about 10 times the size of the internal capacitance specified in the datasheet. Now I'm using a 2N3904 here, which has a typical base emitter capacitance of 18 picofarads. So I'd want about 180 picofarads here, just so that this is really shunting out that capacitance effectively, and you're not really concerned with any small variations in that internal capacitance. Now I don't have a 180 picofarad cap on hand, so I'm going to use 150, close enough. So what about C2? Well, very commonly you'll see people set C1 equal to C2, and that's a good starting value because that's going to give you a gain through your feedback network of 2, and usually that's enough to start up oscillation. But obviously you can tweak these as needed in order to get more gain or to set a larger voltage on your emitter here, because again C2 controls both of those properties. So I'm going to start off with C2 set to 150 as well, and now we want to take a look at our loop here and make sure we have enough loop gain in order to oscillate. And to do that, we need to take a look at some of the crystal parameters. So the crystals that I'm using with this circuit are 12 megahertz crystals. They are intended to be parallel resonant with about 20 picofarads, but I don't actually have the datasheets for them because I'm not sure quite where they came from. They do have a 20 picofarad stamped on them, which is how I know the capacitance they're intended to be used with. but otherwise I don't really have any information on them. I just have a bunch of them in the parts bin. But that doesn't really matter too much, because the reality is what we're really concerned with in terms of the crystal parameters is that internal resistance, RE, because that's, shows up in all the equations that we've been working with. However, that's not specified in any datasheet anywhere ever. Unless you're working very closely with the crystal manufacturer or you're sitting down and measuring each crystal, you're not going to know what RE is. So usually what you get in the datasheet is an equivalent series resistance, and it's a maximum equivalent series resistance. And for a 12 megahertz crystal, it might be something like 40 ohms. So this is really just an approximation. You don't really know what the ESR is going to be. For a parallel resonant crystal like this, the actual internal RE is going to be a little less than this, but it depends on the load capacitance you have across it, as well as the shunt capacitance inside the crystal, which is usually about 5 picofarads. So I usually just use the maximum ESR as the RE in my equations. It's not that accurate, but it is kind of a worst case scenario, and any calculation we do of the internal RE here, unless we actually sit down and measure it with test equipment, is going to be an approximation and an assumption anyway. So I usually, just for simplicity, use the maximum ESR in place of my RE and plug that into my equations. So remember, our transconductance times the impedance of our C1 and C2 capacitors, which are both about 88 ohms at 12 megahertz here, needs to be larger than the internal resistance of the crystal. And we see that GM times the two impedances of our capacitors is 294, which is 7 times greater than our 40 ohms here. So that's a pretty good gain margin. And also when you consider that this is really a very pessimistic view of the internal resistance of the crystal, because it's actually going to be much lower than that, this is going to be more than enough to ensure that we have enough loop gain for this oscillator to oscillate. So now what about the loaded Q of the crystal? We've kind of set all of this up and we haven't really talked about the loaded Q of the crystal at all. Well, that's going to be determined by the capacitance and resistance seen across the crystal terminals. So what we want to do is take the parallel resistance that it sees and this capacitance that is also in parallel with the crystal, turn them into a series equivalent capacitance and resistance, and make sure that the series equivalent resistance is much smaller than the internal resistance of the crystal. That way we're not degrading the high Q that a crystal normally has when we stick it in the circuit. So the capacitance that the crystal sees is these two capacitors in series, which is going to be 75 ohms total, plus the internal capacitance that it has is going to be in parallel with that, and it's usually about 5 picofarads. So we have a total of 80 picofarads of capacitance that the crystal sees across its terminals, and the input impedance of the transistor is going to be about 48 kiloohms, which is 82 in parallel with 120K. So when you take that of 48K in parallel with 80 picofarads, convert it into a series equivalent circuit, you get this, which is 80 picofarads and very low resistance of about 0.6 ohms, at least here at 12 megahertz. So this is very good. This nice low resistance means we're going to add relatively little resistive losses, which keeps the Q high. However, this capacitance is much higher than the 20 picofarads specified for the crystal. Now, in this case, I don't really worry about that, so I'm going to leave it as is. If I really wanted to make sure that I was operating right spot on frequency, I could add a capacitor in series with the crystal here, and it's usually you'll put in a trimmer capacitor here so you can trim it spot on frequency if you really need frequency accuracy there. So I think this will make a pretty reasonable oscillator. We certainly have plenty of gain in order to ensure oscillation, and we should have a nice high loaded Q for the crystal as well. So let's head on over to the bench, build it up, and make sure it works. So I have all the DC biasing set up here with the resistors and the transistor. And so before I actually add the crystal to get the thing to oscillate, I want to just check my DC parameters here. I should have 9 volts on the power rail. The base voltage should be about 5.2 volts. If I can get on there. Yeah, 5.18, that's pretty close. And the emitter should be about 4.5, 4.6 volts here. 4.57. So that all looks good. Everything seems to be biased properly. So I'll add the crystal in and we'll see if we can get it to work. All right, everything should be ready to roll. I've got channel 1 on my scope hooked up to the emitter of the transistor and channel 2 hooked up to the base so we can monitor the voltages there when we turn this thing on. So let's head on over to the scope and make sure this thing actually oscillates. All right, let's apply power. And we've got oscillation right here at 12 megahertz. Now you'll notice that these are not very sinusoidal waveforms. And that's not terribly uncommon for Colpitts oscillators. Once the amplitude reaches this steady state, the transistor actually spends very little time in its linear region. Most of the time it's spent either in cutoff or saturation. So you do get kind of distorted waveforms out of most Colpitts oscillators. If you really want a nice clean waveform, you can often stick a capacitor between the crystal and ground, and you can tap off of the junction between the capacitor and the crystal. The problem with that is that's very high impedance point, so you usually need a very high impedance buffer connected there. Whereas if we take the signal off the emitter here, which is channel 1, then you get a nice low impedance output. However, you may need to filter the output if you need a nice sinusoidal, non-distorted, non-harmonic waveform. But we can look at the voltage between the base and the emitter, and with the 2 capacitors we've chosen, both of them being equal in value at 150 picofarads, we'd expect that the base would be twice the voltage of the emitter. And we can see that it's almost spot on twice the voltage here. We've got 1.36 volts peak to peak on the emitter and 2.6 volts peak to peak on the base. So that's almost exactly what our calculations would have predicted. One of the things to be wary of is I'm actually probing the base of the transistor here on channel 2. And that means that my probe is hooked directly across the crystal because the crystal is connected between the base and ground. So watch what happens to the emitter voltage when I disconnect that probe from the base. Well, if I can get it disconnected, there we go. You'll notice that it jumped up to 1.8 volts peak to peak. So by putting that probe across the crystal, we were actually making the oscillation smaller. The amplitude of oscillation is smaller. So if you want to know what the voltage across the crystal is, usually it's best to just probe the emitter and then apply the equations that relate the emitter voltage to base voltage, which is just that voltage divider equation. So what if I wanted a little more voltage out of my emitter? Maybe 1.8 volts isn't quite enough. Well, I can lower the C2 capacitor. If I make it a smaller value, it'll have a higher reactance, and while that will decrease the gain of our feedback network, it will increase the voltage drop seen at the emitter because we have a larger impedance there between the emitter and ground. So I replaced the 150 picofarad C2 capacitor with an 82 picofarad capacitor, and we can see we now have 3 volts peak to peak on the emitter. And if we look at the base, you can see that it's larger as well at 4.65 volts, but because we've decreased the value of C2 and thus increased its impedance, the difference between the base and the emitter is not as large as it was before, and that's perfectly acceptable. Now, because I'm probing the base at the moment with channel 2, we should actually have a little more voltage than what we're showing right now on the emitter once I remove that probe. And you can see we're up at 4.3 volts peak to peak now that I'm not loading down that crystal with my channel 2 probe. Now, one final thing to verify is that you're not dissipating too much power in the crystal. Now ideally you would do this by putting a current probe here and measuring the current through the crystal, and then power is just current squared times the internal resistance of the crystal. But a lot of times you don't have a current probe, I certainly don't, so the next best thing is to calculate the voltage across the crystal, and we should get 3.6 volts peak to peak with those 250 picofarad capacitors, because with those two in there we were getting 1.8 volts peak to peak here on the emitter, so the voltage at the base should be twice that. And we can then just calculate the current based on the impedance of the crystal. Since the crystal is going to be resonant with the capacitance that it sees across its terminals, it will be resonant with the two series capacitors here, C1 and C2, plus its own internal capacitance C0, which is about 5 picofarads. So you can add those two impedances together to get the impedance of the crystal, convert the volts peak to peak into volts RMS, divide to get your current, and then square that and multiply it by the internal resistance of the crystal. So in this case, assuming worst case scenario 40 ohms of resistance inside these 12 megahertz crystals I'm using, we're actually dissipating about 2 milliwatts in the crystal. And that's a little bit high. Typically these are rated for a maximum drive level of 100 to 500 milliwatts. Now you can't exceed that drive level. You're not going to break the crystal by putting 2 milliwatts through it. But you do have to be cognizant of a few things. The more power you dissipate in the crystal, the more internal heating is going to occur, and that's going to cause crystal drift at startup until it kind of heats up and acclimates. The other thing that will happen is that this will exacerbate aging effects. So the crystal will age faster than a crystal run at a lower drive level. So you can get away with higher drive levels if you really want more power output, and you may need that, especially if you want a really low phase noise oscillator, because phase noise is really just a signal to noise ratio. So the larger your signal, the better your signal to noise ratio is going to be. But you do have to take into account that you're going to have worse aging effects and possible drift due to internal heating. So that video ended up being a lot longer than I expected it to, but hopefully you have a better understanding of how Colpitts oscillators work and how to design one. As always, if you have any questions, suggestions, or corrections, please leave them in the comment section below, and thanks for watching.